Hello, and welcome to the 2026 URC System Acceptance Review for the RIT SPEX Rovers team.
Our team is located in Rochester, New York, and is comprised of over 25 members from diverse backgrounds in electrical, mechanical, and software engineering.
We are proud to introduce our new and improved Scorpio Rover for the 2026 competition season.
The Rover's drive system has seen significant improvement since last year. We switched from the experimental 6-wheel crab suspension to a new 4-wheel rocker suspension with shock absorption and springs on each wheel. Switching from 6 to 4 wheels allowed us to increase the size of each wheel from 6 inches to 12 inches, which makes traversal over obstacles much easier. The tires have an aggressive tread pattern, which gives them traction in sand, dirt, or snow. The new suspension design also lowered the center of gravity about 6 inches, which reduces the risk of tipping over. As a result, the Rover can climb steeper slopes than it could in the past, and it can turn in place without problems. We kept the vertically mounted motors with bevel gearboxes in order to keep the motors away from potential obstacles close to the ground. The Rover's quick swap system allows the autonomous, arm, and life detection modules to be mounted and removed in under a minute. 4 thumb screws hold the modules to the Rover, and aviator connectors are used to supply power and control signals.
Similar to last year, our arm has 5 axes of motion with carbon fiber hexagonal tube supports, which maximize strength and stiffness while minimizing weight. The elbow, shoulder, and base joints are controlled by high torque harmonic motors, which allow us to easily pick up over 5 kilograms. All of the motors on our arm feature built-in absolute encoders, allowing us to use a space mouse to more accurately and intuitively control the position of the end effector. Through the use of 2 high-precision servo motors that drive the bevel gearbox wrist joint, we are able to actuate the end effector both vertically and rotationally, making flipping switches and turning knobs easy. The end effector has been completely redesigned this year, moving from a 2-jaw angular gripper to a 3-jaw lead screw gripper with foam-padded fingers that is controlled using a DC servo module. The 3 jaws helps grasp round objects such as the camlock hose fitting.
This year, we have fully implemented an inverse kinematics-based control scheme, making control of the end effector much smoother than in previous years. With this, we can easily plug in a USB drive, put a test tube in a holder, and more. We have attached a solenoid to one of the fingers of the gripper. This allows us to more easily press buttons and type on a keyboard.
The Rover's autonomous navigation capabilities have been significantly improved over the past year. In addition to AR tag tracking, the Rover can now execute a search path to find 2 types of hammers or a water bottle. First, the search path algorithm generates a path and uses IMU orientation data with proportional control to keep the Rover on that path. Once an object is spotted, the Rover will exit the search path, drive to the object, and stop. The object detection system uses a custom-trained YOLO computer vision model which runs fully on board the Jetson. The Rover also has the ability to travel to a specified GNSS coordinate. The Rover's GPS module connects to 4 GPS constellations and has an impressive positional accuracy of 1.5 meters, which is more than enough to get us to the locations of interest where either the AR tag detection or object detection can take over. Additionally, we will be implementing differential GNSS with another GPS module on the base station for improved accuracy. Finally, the Rover's obstacle avoidance system has been upgraded. The LiDAR's point cloud is converted into a 360-degree laser scan, which is then used to autonomously steer the Rover away from obstacles.
Our life detection module begins with a custom-built auger fitted with a hardened steel tip to drill into the soil. As the auger drills downward, we plan to have a long spike-like probe simultaneously pushing into the ground to gather deeper subsurface data. The first system performs a ninhydrin test, which is designed to detect amino acids. A micropump deposits tiny amounts of the liquid sample into test tubes that already contain the ninhydrin reagent. The mixture is then heated and gently agitated. If amino acids are present, the solution changes color to Rumen's purple, a strong potential indicator of biological activity. Our second system is an absorbance spectrometer built around a Hamamatsu mini spectrometer. After calibrating the instrument with distilled water, we analyze the absorbance spectrum of the dissolved sample. These results are compared against a database of known substances. The database primarily includes common minerals to help us understand the geological makeup of the area, but it can also be expanded to include key molecular building blocks of life. While the soil samples are being processed, the rover captures a panoramic image of the sampling site. We combine this visual data with the spectrometer results to better understand the mineral composition of the surrounding terrain.
The rover's main computer is an NVIDIA Jetson Orin Nano. This is responsible for processing arm and life detection controls and data collection, as well as chassis data through a custom-designed main bodyboard. Each of these subsystems has its own dedicated Teensy microcontroller that communicates with the Jetson via CAN. The rover communicates via a 900 MHz radio transmitter. The video data is transmitted via 2.4 GHz signal.
The rover's base station is new this year. Its main board is a Raspberry Pi 5. The base station can be powered either through barrel jack or by an internal battery that provides up to 6 hours of runtime. It has a small screen to provide data about connection and information being sent and received.